So we have finished this part, and we finally got the equation for current at resonance when you consider the condition XL equal to XC to be equal to V by R. So if you observe this equation is showing that at resonance this circuit is a pure resistive circuit, and at resonance you can observe that the impedance Z is equal to R. That is because XL is equal to XC, so this term gets cancelled and the impedance Z will be equal to R. So sometimes they might ask you the question, say, prove that impedance Z is equal to R at resonance for a series RLC circuit. So you need to do this particular derivation. Okay. So the question can be asked in this way also, or they might just ask you derive the expression for current I in the case of a series RLC circuit. So moving on, we were into obtaining the graph of frequency response of the series resonant circuit. Okay, so beginning with the equation for the current I, we have seen previously the equation for the current I is given as I to be equal to V by R at resonance. So at resonance, this I equal to V by R corresponds to the maximum value of current, which is represented as Im. So let us see what happens when we have different values of omega, and what will be the graph when the angular frequency omega is very less, when it is very high. So before that, let me consider the expression for reactance of the inductor in terms of omega, that is equal to omega L, and the capacitive reactance Xc in terms of omega, that is equal to 1 by omega C. Now if omega is equal to 0, then you can see XL is equal to 0 and Xc will be equal to infinity. So therefore I can say that the capacitor in the series RLC circuit will be acting as an open circuit, and you have the current that will be flowing in the circuit to be equal to 0. If omega is equal to infinity, then XL will be equal to infinity and Xc will be equal to 0. In this case, the inductor will act as an open circuit, and again current will be equal to 0. But at XL equal to Xc, we have seen previously the current is equal to Im, which is equal to V by R, and this current corresponds to the maximum value of current. Now we need to check the condition as to what happens when XL is greater than Xc, and what happens when Xc is greater than XL. So when XL is greater than Xc, if you look at the expression for current, we have it as I to be equal to V by Z, or in terms of resistance and in the presence of inductor and capacitor, it is V by R plus J XL minus XC. So if XL is greater than XC, then the circuit will be a inductive circuit, because the value of resistance is constant. So if XL is greater than XC, then the circuit is inductive. If XC is greater than XL, the circuit is capacitive. Now, before we get into the graph, I said we need to analyze what happens when XL is greater than XC and what happens when XL is less than XC. So for that, let us write the expression for the reactance XL and XC. So you can see here, XC is given by 1 by 2 pi FC, and XL is given by 2 pi F into L. The capacitive reactance is inversely proportional to the frequency. So if the frequency is decreased, okay, if the frequency is decreased, since it is inversely proportional, the capacitive reactance will increase. And if the frequency is increased, then the capacitive reactance will decrease. For the case of the capacitor. Whereas if you consider the inductor, when the frequency is decreased, the inductive reactance also will decrease, and when the frequency is increased, the inductive reactance will also increase. So clearly we can find out or show in the frequency response what happens when the frequency is lower and what happens when the frequency is higher. So let me draw the graph. This is a graph of current versus frequency. I can consider in terms of angular frequency also, not required that it has to be in terms of the frequency itself. I can represent in terms of omega also. Okay. Here I have considered in terms of omega. You can consider in terms of omega, if not in terms of frequency, because omega is equal to 2 pi f. So when I say at resonance, that is at resonance XL equal to XC, means in terms of frequency f, it is at f naught. Okay. Or I can say it is at omega naught in terms of angular frequency. So if I consider the resonant frequency as f naught, we have obtained from the derivation that you obtain the maximum value of current Im at resonance. Correct? So this is the maximum value of current that you obtain. Then you can see we have seen from this expression that if XL is greater than XC, the circuit is inductive, and if XC is greater than XL, the circuit is capacitive. Correct? And we have also seen from the expressions here as to what happens when frequency is decreased for a capacitive reactance and what happens when frequency is decreased for a inductive reactance. So if you observe the graph, at omega naught equal to 0, or I can say at omega equal to 0 or f to be equal to 0, I obtain the current I to be equal to 0. So if F is equal to 0, I obtain the current to be equal to 0, and if F is equal to infinity, then again I obtain the current I to be equal to 0. So I know that my graph has to be in such a way that you obtain a 0 at this point and you obtain a 0 at this particular point. So I can finally draw this as in this form. Okay, at F equal to 0 or omega equal to 0, current is 0. At F equal to infinity, current is equal to infinity, and I obtain the maximum value at resonance when F is equal to F naught. Now what about this case? Because I know at this point it is XL equal to XC, right? So what about this region, that is when F is less than F naught and when F is greater than F naught. So when F is less than F naught, you can see here from these expressions what we have. You have that the capacitive reactance is higher and your inductive reactance is lower. So at this region your capacitor is acting more comparative to the inductor. So in this region, let me change the color to indicate that. So in this region it is XC greater than XL, whereas in this region when F is higher, the capacitive reactance is lower and the inductive reactance is higher. So you have XL to be greater than XC. When F is equal to 0 and when F is equal to infinity, the current is 0, but in other places you can see which is acting more in comparison to the other, whether it is the capacitive reactance or whether it is the inductive reactance. And the resonance condition is obtained at this particular peak XL equal to XC, where the current is maximum. Clear? So this is the frequency response of the series circuit. Okay. Now let us see what we can do to the equation for current so that we obtain a higher value. Okay, what modification can be done to the current if we want to obtain a higher value? Till here, is it clear? Anyone is having any doubts? How we have obtained this graph, is it clear to you? Yeah, audible, right? One minute. Yeah, yes, okay, fine. Clear. So moving on, let's see what happens if we want to have higher value of current. Okay, so we have the expression for current I to be equal to V by R plus J XL minus XC, and at resonance when XL is equal to XC, we obtain I to be equal to V by R, that is a pure resistance. Now we need to we need to have, or what we want is, we want to have a higher value of current. So the applied voltage is constant, so the only option that you have is you need to vary the resistance. So I can vary the resistance, and for different values of resistance I can obtain the current. So let me draw the graph wherein I have different values of resistance and the change that you observe. So now let me plot the graph of current versus omega. Okay, omega is the angular frequency. I've told you earlier also. The frequency response of the circuit can be plotted either in terms of frequency or in terms of angular frequency omega. Okay, so this was my normal curve that I had, and here I will denote at resonance, and this was obtained as the max value Im. Let me consider three different values of resistance. If you look at the equation for current, okay, this is equal to Im. So Im can be written as V by R. If I am going to decrease the resistance, I can obtain the increase in the equation for current. Correct? The current can be increased if you decrease the value of resistance. So what happens in this case is, higher the value of the resistance, the greater will be the current. That is because if the denominator is higher, then you will get this resultant to have a higher value. Correct? So if I consider the next graph, this will be the new value of the current with the peak here. I can consider another graph with a different value of resistance. So I can obtain my peak at this particular point. So if I consider, say, the three resistances R1, R2 and R3, what will happen? Can anyone answer? Say I consider this is because of resistance R1. This initial graph which I have drawn in white color is because of the resistance R1. Can kindly type in the chat box, because sometimes I cannot hear your voice. Okay, if I consider this to be R1, then this red color one to be caused by the resistance R2, and the yellow color one caused by the resistance R3. What will be the relationship between R1, R2 and resistance R3? So as the resistance decreases, the current increases. Correct? So what is this relationship? You have resistance R1, you have resistance R2 and you have resistance R3. So the value of which resistance has to be greater? Can you tell me? It will be R1 less than R2 less than R3. So you can see here the value of the resistance as it decreases, you will get the curve in this particular form. Okay, so the resistance R3 should be greater than the resistance R2, greater than the resistance R1. Clear? Yes. Okay, fine. Moving on, let us look into the phasor diagram. Okay, the phasor diagram. Now we are focusing on at resonance, right? So at resonance we have the inductive reactance to be equal to capacitive reactance. So I can plot the graph of voltage versus current. So at resonance, your current and voltage are superimposed, whereas the voltage of the inductor VL will be advanced or lead by 90 degree, and the voltage across the capacitor will lag by 90 degree. The current and the applied voltage will be in phase. So this is the phasor diagram that you obtain. Fine. So next we will move on to obtaining the equation for resonant frequency. So let us consider in this case F0 to be the resonant frequency of the series RLC circuit, and at resonance we have the condition that XL is equal to XC. So therefore, just look at this relationship. We can expand this in terms of frequency. We can write this as 2 pi FL equal to 1 by 2 pi FC, and at F equal to F0, because resonance occurs at a frequency F0, right? We have shown that in the graph here also previously when we considered the frequency. So at F equal to F0, just substitute in this particular relationship. So 2 pi F0 L equal to 1 by 2 pi F0 C. I can write this as F0 square to be equal to 1 by 4 pi square L into C, and let me take the square root of this. This will become 1 by 2 pi square root of L into C. So this is the expression, and the unit is Hertz. Okay, the same derivation can be done in terms of angular frequency. So till here this part remains the same. The relationship will be, if XL is equal to XC in terms of omega, you can represent this as omega L equal to 1 by omega C. At omega equal to omega naught, this will be omega naught L equal to 1 by omega naught C. So omega naught square is equal to 1 by LC, or omega naught equal to 1 by square root of LC. The unit will be in what? Can anyone tell me what will be the unit? What will be the unit? Radians. Kindly don't unmute and say, because I'm having a problem with my headphones. Sometimes I cannot hear. So you can type in the chat box. Okay, it's radians. So to conclude, okay, let me write the conclusion. The first thing that we saw is at resonance, what happens? The condition that we have is XL equal to XC. Secondly, we have seen that the impedance Z is equal to R. Thirdly, we have the current I to be equal to the maximum value, which is equal to V by R. Also, we have seen that the current is in phase with the applied voltage. When you have current in phase with the applied voltage, we have the phase angle to be equal to zero, and hence we can say the power factor cos phi to be equal to 1. So these are the observations that we have made, and they also correspond to the properties of the series resonant circuit. Okay, so if they ask you the properties of the series resonant circuit, we have seen this earlier also. Again, you can dot down these things. Okay, there is one more thing that you can observe here to add. We obtain at resonance the current to be maximum. So if the current is maximum, then you have the power which is given to be equal to I square into R. So here I will be equal to maximum, means I can substitute this as Im square into R. So which will also give me the maximum power P max. So power also is maximum at resonance. Okay. Fine. So moving on, next let us look into the effect of the circuit elements with respect to frequency. We will be drawing the graph for a resistor, inductor and a capacitor in this case, and then we will try to find what is the total response. Okay. So if you look at the graph of impedance versus frequency in the case of a resistance, if I draw Z versus F for a resistor, the value of the resistance almost remains constant unless and until we tend to vary it to obtain the maximum value of current. So this is the graph of impedance versus frequency, because this is not dependent on frequency, right? Resistance is a flat response because it is not frequency dependent. So this is the graph for a resistor. You obtain a flat response. If you look at the inductor, in the case of an inductor, the expression for the inductive reactance is given by XL to be equal to 2 pi FL. So this is directly proportional. You can see that F is directly proportional to XL. Okay, so if frequency is increased, XL also increases, or I can say impedance also increases. If frequency is decreased, XL also decreases. So this graph is a linear graph. Okay, that is because XL is directly proportional to F. Now for a capacitor, let us see. what happens? This is the impedance versus frequency for the capacitor. Okay, so for the capacitor, if you observe, we have the capacitive reactance given by Xc to be equal to 1 by 2 pi f into C. So if you decrease the frequency here, the capacitive reactance is higher, and if you increase the frequency here, the capacitive reactance is lower. That is because Xc is inversely proportional to frequency. So when I draw the graph, you can see for lower frequencies, capacitive reactance is higher, and for higher frequencies it is lower. Okay, so let me now draw the total response. Okay, the total response, which includes resistor, inductor and capacitor. That is because in our circuit we have all of these, right? So the total response when you draw, you need to consider also the condition when there is a resonance. So now I am considering the value of impedance in terms of magnitude. Okay, let me consider the condition of resonance F0. So here Z is equal to R at F0, and we need to see what happens when you have an inductor and a capacitor. Previously, if you look at the graph, when I explained you this concept, I said when XL is greater than XC, the circuit is inductive. That means for higher frequency, your inductor is more responsible, whereas when Xc is greater than XL, the circuit is capacitive. That means at lower frequencies, your circuit is more of a capacitive type of a circuit. So capacitor is responsible at lower frequencies. So when you draw the graph here, you have to consider at lower frequencies capacitor to be playing the major role, and at higher frequencies it is the inductor to be playing the role. So you need to consider the capacitor at lower frequencies. Okay, so draw this graph. Okay, and at higher frequencies it is the inductor, so make it linear. Fine. So do write this somewhere. At higher frequencies and capacitor at lower frequencies. So this is when F is equal to F0, the condition when XL is equal to XC. Clear? Yes. Yes or no? Yes. Okay, fine. Now we'll move on to the expression for bandwidth. Okay. So before we go to the expression for bandwidth, we need to define what is a bandwidth. So bandwidth can be defined as the band of frequencies over which the power of the circuit is half of its maximum value. So let me consider the circuit response and explain you how we have got the expression for bandwidth. So let us consider the frequency response. or the circuit response. This is current I, this is the frequency F. This is a resonant frequency, and I obtained the maximum value Im here. Where Im corresponds to the maximum value of current at resonance. Okay. Now if you look at this particular response, or for that matter any response, output response of a circuit which is frequency dependent, it will have certain limitations. Okay, that is, the limitation is that there are at least two frequencies where the current will be equal to the RMS value. Okay, RMS value is computed as IRMS to be equal to Im by root 2. It is 1 by root 2, the maximum value of current. So in this response also we do have the limitation that at one particular point, or at the two frequencies of this particular response, the current will be equal to its RMS value. So I can consider the RMS value of current Im by root 2 here. So at this frequency and at this particular frequency, the value of the current is same, which is equal to Im by root 2. So in this range, at this particular point, when the current is equal to its RMS value, the output power is equal to the half of its maximum power. Okay, so if I have to show that mathematically, I can write the equation for power P to be equal to I square R. Okay, if I'm considering the maximum power, maximum value of current, I will become Im. At the RMS value, this current I is equal to Im by root 2. So I can write this as Im by root 2 the whole square into R, or I can write this as Im square divided by square root of 2 the whole square is 2 into R. So this is equal to the power at these frequencies. If you consider the expression for the maximum power P max, this is equal to the maximum value of current into the resistance. When you compare this expression with this expression, you can see that P is equal to Im square into R is P max. So this is equal to half of the maximum power. And since at these frequencies you have the power to be equal to half of its maximum power, the corresponding frequencies, I will denote this as F1 and F2, will be termed as half power frequencies. Okay, and this band of frequencies between F1 and F2 is called as the bandwidth. Remember, the band of frequencies between F1 and F2 is called as the bandwidth. So I can represent bandwidth B to be equal to F2 minus F1. This is bandwidth B. So within this range between F1 and F2, the output power, the output power of this particular circuit will be more than half of its maximum power. So within the band, within B, you will have the power to be greater than or equal to half of its maximum power. It is only at these half power frequencies you obtain the power to be equal to half of its maximum power. Within the band, it is greater than or equal to half of its maximum power. So you have seen the definition of the bandwidth, which says the band of frequencies over which the power of the circuit is half of its maximum power, which is obtained from this particular expression, because we can see the limitation of the output response, that at two frequencies the current will be equivalent to its RMS value. Okay, clear till here? Is it clear? Yes. Okay, fine. Now this Im by root 2 can also be represented in terms of 0.707 into Im. Okay, that is because if you substitute or calculate 1 by root 2, you will get it as 0.707 and Im is kept as it is. We can also represent in terms of the logarithmic scale. If you consider the logarithmic scale, then 20 log of this value, 20 log of this value will be equal to 0.707 will be equal to minus 3 dB. Okay, minus 3 dB. So this RMS value here will be equivalent to minus 3 dB if you are considering the logarithmic scale. Okay, so minus 3 dB from its maximum. And sometimes these frequencies F1 and F2, I have told that they are specified as half power frequencies, or they can also be called as the cutoff frequencies, because your band is between F1 and F2. So they are also called as cutoff frequencies, and this will be your lower cutoff frequency, this will be your higher cutoff frequency. Remember, lower cutoff, upper cutoff, or higher cutoff. That is why we said, if you want to obtain the current to be maximum, if you saw this graph, if you want to obtain the current to be maximum, then the band has to be narrower. You can observe here, right? The band has to be narrower. Whereas if you say or look at the first graph, which is shown in white, the band was wider, then it was little narrower, and when you look at this yellow graph, you can see the band is still more